Today, I will demonstrate how to express a number as the sum of two squares using Fermat's theorem. I'll walk you through the principles behind this step by step to ensure you fully understand. Please make sure you follow along till the end. Before we begin, you can take a moment to subscribe and like my content. Okay, let's get started. Does every number have a representation as the sum of two squares, and how would you represent it? Can we write it in the form of x squares plus y squares, where x and y are integers? Let's take a look at some smaller numbers, and you'll find that not every number can be expressed as the sum of two squares, like 14, 15, and 19. Why can't they be expressed in this way, and what do they have in common? In additive number theory, Fermat's theorem on sums of two squares states that an odd prime p can be expressed as p equals x square y square with x and y integers, if and only if is identical to 1, mod 4. It means that, for example, 5 is an odd prime number, and when divided by 4, the remainder is 1. Therefore, it can be expressed as the sum of two squares. There are other odd prime numbers like 13 and 17, and they can also be expressed as the sum of two squares. So, we can conclude that all odd prime numbers in the term of 4k plus 1 can be expressed as the sum of two squares. Given a simple example, 1234, we want to express it as the sum of two squares. First, we'll decompose it into prime factors. 2 itself can be represented as the sum of two squares. Notice that 617 is an odd prime number, and it also gives a remainder of 1 when divided by 4. So it can represent it as the sum of two squares. Now we're stuck, we've encountered a rather complex factorization. How do we simplify this? We know that some basic algebraic expressions like a square minus b square can be expressed as a plus b times a minus b. If we substitute it with a square plus b square, how would we express it? We need to incorporate the imaginary number I. Let me briefly explain. I is the square root of minus 1. When I is multiplied by itself once, we get minus 1. So, we can add I in place of b. -1 times -1 will become positive, thus resulting in a square plus b square. Now we can conjugate it. We find out a square plus b square equal to a plus bi times a minus bi. Remind that earlier we only decomposed a square plus b square. But in this case, it's sum of two square time another sum of two square. If we directly decompose it, it will become quite complex. But we can rely on conjugate complex numbers to solve it. When we need to express the product of both sums of two squares in the form of x square plus y square, we express each of them as their respective conjugate complex numbers. Let's rearrange it. Start to express it. A times c. Notice that bi times di, I, times I, become -1, so it become minus bd. A times di plus bi times c. We just arrange it. Then on the other side, we follow the logic I just explained. Now let's observe it. You'll find that it looks like a conjugate complex number form. So, we can express it as the sum of two squares. Going back to the initial problem, when we plug in the expressions, it simplifies a lot, and we can find the sum of two squares for 1234, which is 3 square plus 35 square. Now you've grasped the basic principles behind these. Another example, 4321. When expressed in smaller prime factors, we find out that both 29 and 149 are odd prime numbers, and they give a remainder of 1 when divided by 4. So, we can express it as the sum of two squares. Next, we can reverse one of the odd prime numbers sum of two squares, and then you'll find the other sum of two squares for 4321. Thus, we can use this method to find all the sum of two squares for 4321. Let's look at a special case, the prime factorization of 2550. 3 is an odd prime factor, but it doesn't give a remainder of 1 when divided by 4, and it doesn't appear twice. What does this mean? When we say 3 appears twice, it means that 3 is multiplied by itself, indicating that it can be expressed as the sum of 2 squares because it's a square number itself. Thus, in this case, for 2550, it cannot be expressed as the sum of 2 squares since the prime factor 3 does not meet the necessary conditions. Look at 1305. Although one of its prime factors doesn't meet the first condition, if it appears twice or the number of times it appears is even, it can still be expressed as the sum of 2 squares. In this case, it's 3 square plus 0 square, so the number 1305 can express as sum of 2 square. Let's quickly look at some smaller numbers. For 12, its factors are 2 times 2 times 3. They are all prime numbers, but 3 doesn't meet the necessary condition. So, 12 cannot be expressed as the sum of 2 squares. What about 18? Since its prime factor 3 appears twice, it can be expressed as the sum of 2 squares. There are 2 possible sum of 2 squares for 25. From here, we can gain a deeper understanding of how it works. By now, I believe you understand how to determine whether a number can be expressed as the sum of 2 squares and how to express it if it can. Finally, we can challenge ourselves with a larger number. We decompose it into prime factors, and all these prime factors meet the condition. However, the number of factors of the sum of 2 squares is too large. How do we solve this problem? Earlier, we elegantly expressed the product of the sum of 2 squares. What if there are even more to multiply? Let's not forget that it is also a sum of 2 squares itself. We just need to express it layer by layer, gradually. Understanding this principle, I've already calculated one of the sums of 2 squares. I'll leave the calculation of the other sums of 2 squares to you. Feel free to leave a comment below if there are any errors or if you'd like to add anything.